This is the first lecture for Chapter 12, and we will concentrate on alkenes and alkynes in this lecture. Notice the names are pretty similar to alkanes which were covered in the previous chapter. The only difference is that we have here an E replacing the A for alkanes, and for alkynes we have a Y replacing the A that was used for alkanes. So look out for that. The only difference in the name is replacing the A with an E for alkene and replacing the A for a Y for an alkyne. But let us get started. What we'll cover in this lecture is the structure and nomenclature of alkenes. So now you'll see the structure and the naming of these type molecules. Then we will look at the structure and nomenclature for cycloalkenes. Notice again the E, alkenes, different from alkanes. Then we will look at the structure and nomenclature for alkynes. Again, alkynes with a Y. And lastly, we look at the properties of alkenes and alkynes. So let us see what really is an alkene. An alkene is a hydrocarbon that contains one or more carbon-carbon double bond. For this class, we'll concentrate only on one carbon-carbon double bond. So the simplest, as you can imagine, here is our carbon-carbon double bond, and the simplest is putting hydrogens on those two carbons of the carbon-carbon double bond. That molecule is known as ethylene, and it is an alkene with an E. Based on the VSEPR theory, the valence shell electron pair repulsion theory, we'd expect this bond angle here to be 120 degrees. So it is a flat molecule. The key here is it is a flat molecule where this double bond here is very rigid, no rotation, and the bond angles here are 120 degrees. The reason why I was emphasizing flat and rigid is that this bond cannot rotate. So there's no rotation here. So we have two isomers, or two possible isomers. One in which the R groups, here is a methyl group, and the methyl group are on the same side of the double bond. As you know, if groups are on the same side, the term we use in chemistry to describe the same size is a cis. So we say this is a cis isomer. A cis isomer alkene. Here's another way of drawing it. Notice that's a methyl group, and that's a methyl group, and there is a hydrogen here that's not written because that is the line angle representation, and another hydrogen that is not written. Here is the representation using a model. So here's the methyl group, and here's the methyl group on the same side, so that makes it a cis isomer. There's another isomer where the methyl group can be on opposite sides of the double bond. It's a different molecule and known as an isomer. Remember here that isomers have the same chemical formula, but the bond-to-bond connectivity or the orientation in space are different. This molecule is different from this one because the methyl group here and this methyl group are on opposite sides, and of course, as you know in chemistry, if groups are on opposite sides of a plane, we say that is the trans isomer. So this is the trans isomer. So again, it can be written like this, using the line angle, where there's a hydrogen here, and there's another hydrogen here, and since there are 4 bonds to a carbon, that's it. Because we have a methyl group here and a methyl group here, that's an opposite side. Notice the drawing, because you will be asked to draw formulas or structural formulas using line angle, and you'll have to be very careful in drawing them so that you get the cis and the trans represented. Let us look at a couple more examples here. Here is the double bond. Here's the double bond right here. And sitting across the double bond are 2 chlorines. So therefore this is a trans isomer of that molecule. Here's another molecule or isomer, the same molecular formula, but the arrangement of the atoms across the double bond is different, so therefore this is a cis. Here's one that you are familiar with in biology, from biology. Here is the double bond, and we have a carboxylic acid group and another carboxylic acid group that are on opposite sides. If they are on opposite side of the double bond, that molecule is fumaric acid. If they are on the same side of the double bond, that molecule, which has the same molecular formula, is maleic acid. So these are isomers, and of course, as you know from biology, the body can recognize these isomers as different. Let us look at some natural products here. So we have here is a saturated fatty acid. Saturated here, which means that there are no double bonds. Notice for this molecule here, there are no double bonds in terms of carbon-carbon double bonds. This is a carbon-oxygen double bond, but we're looking here at carbon-carbon double bond. There are none in this molecule here. For oleic acid, though, here is a carbon-carbon double bond right here. And the question is that a cis double bond or is it a trans double bond? You can see from the way it's drawn, it is a cis double bond because this group here and this group here, they're on the same side of that carbon-carbon double bond. Don't forget we have 2 H's here that are not written in because we're using the line angle representation. So this is a cis double bond. Linoleic acid, it has 1 double bond, 2 double bonds, and 3 double bonds. So we say it's polyunsaturated. Notice unsaturated here means it contains double bond. This is a mono unsaturated because it just has 1. This is poly because it has more than 1 double bond in the molecule. Notice again, they're all cis, double bond. And this one here is a cis double bond, and of course this one is a cis double bond. So the cis arrangement around it. Let us look at another molecule here, vitamin A. Let's look at this double bond, for example. This double bond here is a trans double bond, because here's a double bond, here's one R group right here, and here's the other R group. Don't forget that there is a hydrogen here, and there is a hydrogen here. So you can see that is the trans arrangement of the double bond. So once again, when you're asked to draw the structural formula using line angle representation, you have to be very careful that you draw the double bonds like this if you want a trans isomer, and the double bonds like this if you want your cis isomer. So be careful with those drawings. Okay, let us see how we name alkenes. The nomenclature of alkenes, and we'll say it is the IUPAC. Remember, we have an international union of pure and applied chemists that formulated the nomenclature of organic molecules. So let us look at the nomenclature of alkenes. Notice again that it has the E. Alkenes indicate the double bond. So once you have identified a molecule that has a double bond, it is an alkene. So you change the A from the corresponding alkane to E. So it becomes an alkene. More specifically, you count the number of carbons in the longest chain. The trick here is you'll have to start at the end that's closest to the double bond. So you start here and not here, because as you can tell, this end is furthest from the double bond. So once you start here, this is 1, 2, 3, 4, and 5. 5 carbons, an organic molecule that has 5 carbons. The corresponding alkane is pentane. But we know that we changed the A to an E as shown here. This E means that we have a double bond in the molecule. Why do we number them? We number it because this 2 here indicates the position of the double bond. So the name of this molecule becomes 2-pentene. When you write these, make sure you write it legibly so the graders can see that this is an E and not an A, or we'll see later on, not a Y. Let us apply it to this molecule. So let's say you're asked to name this molecule here. Here is the double bond. So we know that it is an alkene. What's the root name for that? We start numbering from the end closest to the double bond. So we start here. That's 1, 2, 3, 4, 5, and 6. A alkane or hydrocarbon that has 6 carbons is an hexane, but since it has an alkene, we change that A to an E, so it becomes a hexene. The double bond is in position number 2, so we have to indicate the position of that double bond by that number 2. So this becomes the name, the IUPAC name of this molecule here. Okay, let us see how we name branched alkenes. Still dealing with alkenes. How do we name branched alkene? Here is an example. This is an alkene because we have the double bond in the molecule. We start numbering at the end closest to the double bond, so we'll start with number 1 at this end and not over here. So we go 1, 2, 3, 4, 5, and 6. 6 represents hexane, but we will change the E, the A for the alkane to an E, and here it is. We'll have to indicate the location of the double bond by that number 2. We have a branch, which is a methyl, since it has 1 carbon. So we have to include that methyl, and we'll have to indicate the location of that methyl based on that number. So once again, you will have to start numbering from the end closest to the double bond and not the branch, as we did when we're naming alkanes. So the double bond takes priority over branching in terms of where we start numbering. Let's see if we can apply that to this example here. So let's see if we can name this molecule here. Here is the double bond. So again, you have to do a systematic approach, observation. Make sure you identify the functional group. The functional group here is a carbon-carbon double bond. Here is our carbon-carbon double bond. We start numbering at the end closest to that carbon-carbon double bond. Notice at the end. So we go 1, 2, 3, 4, 5, and 6. Again, it's a hexane, but we change the A to an E to indicate here that we have a double bond. Next, we have to indicate the location of the double bond. That's on carbon number 2. So this carbon number 2 is to represent the location of the double bond. On carbon number 5, we have a methyl group and another methyl group, so it's a dimethyl. And of course, both methyl groups are on number 5, so we say 5, 5. Notice it's not just 1, 5, but 5, 5, because it is a dimethyl. So you should be able to name alkenes and branched alkenes. Some more examples. Here is a alkene, line angle. Here's a double bond. So we start numbering at the end. It so happens that the end here has the carbon of the double bond, and we go in this direction, 6 carbons. So it's a hexene. Change the E, A to an E, and this 1 represents the location of the double bond. Same here. Double bond is right here. Start in this direction. Start here and go in this direction. Again, hexene, and this 1 represents the double bond. But here we have a methyl group, and it's on position number 4, so it becomes a 4-methyl. Same here. Start at the double bond. Identify the double bond. Start and go in the direction of the double bond and find the longest chain. This is an ethyl bonded to the longest chain, however. And here is another ethyl bonded to the longest chain, which is right here. So we have a diethyl, 1 ethyl, 2 ethyls, a diethyl. They are on carbons number 2 and carbon number 3. So it's a diethyl, and the position of the double bond is 1 for the pentene, because it's 5 carbons. So once again, you have to be really, really observant to identify your double bond, identify the location of the double bond, start numbering close to the end of that double bond, and determine the root or the corresponding hydrocarbon based on that table we learned in the last chapter, and come up with the IUPAC name. Let us turn our attention now to cyclic alkenes. Cycloalkenes. How do we name that? Pretty straightforward. First of all, you have to have a ring, as we have here, and you'll have to have a double bond to have a cycloalkene. Notice again, E, cycloalkene. How do we name it? Well, we identify the double bond. Here's a double bond. One of these carbons will be number 1. Notice one of these carbons will be number 1, because a ring, of course, has no start or no end. So one of these is number 1, but once you have determined that this is your number 1, you have to go in the direction of the double bond. So it's 1, and then 2, 3, 4, 5, 6 represents cyclohexane, but of course we have a double bond, so we change the A to an E, so it becomes a cyclohexene. Be careful when you write these names that you make it legible, that the E can be read by the graders. Here's another molecule. It has, the double bond is right here. So one of these carbons can be number 1. I've chosen this one to be number 1, so we have to go in that direction. We have 5 carbons, so it's a cyclopentene. Notice we need not put 1 here, because it's understood to be in position number 1. If you put it, it's not incorrect, but it's not needed. Let us look now at branched cycloalkenes. So if there's a branch on the ring, how do we name it? Here's an example. So here's a 6-membered ring. Here's a double bond right here. So we'll have to start at this, either this carbon or this carbon. Now we're locked into numbering so that we go in the direction of the branch. So if we'll have to start here at number 1 and number 2 and number 3, because the branch is here, so we have to go in the direction of the branch. Make sure the branch is closest to the double bond. So in other words, you would not start here as 1, because you can see if you went in this direction here, the branch would be furthest. So you do not go in that direction. So the direction that you go is 1, 2, 3, 4, 5, and 6. 6 would be a cyclohexene. The double bond is in position number 1. You can leave it out or include it. But more important is that this methyl group here is in position number 4. And here's that 4. So you will have to indicate the location of branches. So notice here you can include the 1, or you can exclude the 1 as shown here. Either one is acceptable. Either name is acceptable. Let us see if we can apply that concept over here to name this molecule over here. First observation, double bond. So as we said, one of these carbons will be number 1. But if we have branches as we have here, we have to go in the direction of the branch. So we are stuck into going in this direction. So this is 1, 2, 3, 4, and 5. 5 would be a cyclopentane. Since it's a double bond, it would be a cyclopentene. Again, you can put the 1 to represent the starting point. We have 2 methyl groups and a methyl group here. So that's a dimethyl, and these 2 groups are on carbon 3, so we say 3,3. So we can write it as 3,3-dimethyl cyclopentene. Make sure the E is legible so we can read it. Okay, here's a couple more examples before we give you a test question here, a quiz question. So here is the double bond. We start at one of these carbons. Here's the branch. So this will have to be number 1. So we have to go in this direction. So 1, 2, 3, 4, 5. And it becomes a 3-methyl, because that's a methyl group, cyclopentene. Another example. Double bond. So one of these carbons will be number 1. So here's a branch, so more than likely we'll start here and we'll go in the direction of the double bond and towards the other branch. So this is an ethyl, as you will see, because it has 1 carbon, 2 carbons, so it becomes an ethyl. And here's the ethyl. It's on carbon number 4, so we have to indicate that as 4. And of course, here's a methyl, CH3, methyl. So therefore, that's a 1-methyl, and of course, cyclohexene. Make sure you write these so we can read it. Okay, let's look at some examples at a quiz type question. Give the line angle structure of the molecule that has the name this. 3-ethyl 5-methyl cyclohexene. Looks like a long name, but as you can see here, it's just a matter of combining the different portions of the molecule. My suggestion is start at the end over here. So this is a cyclohexene. So it is a 6-membered ring with a double bond. So you can see right away this is not work. So what you may want to do here is to number 1. If you call this number 1, this is number 2, number 3, number 4, number 5, and number 6. Now, all you have to do is put these groups on. Carbon number 3 has an ethyl. So carbon number 3 has an ethyl. Notice that's an ethyl. And carbon number 5, we have a methyl, using the line angle representation. So you can see that this is not the molecule, doesn't look like this. This is not the molecule, does not look like this. This one, however, looks pretty close. So let's make sure. So let's number this. 1, 2, 3, 4, 5, and 6. And you can see that on carbon number 3 is a ethyl. Carbon number 3 is an ethyl. Carbon number 5 is a methyl. Carbon number 5 is a methyl. So these two molecules are the same. So again, you have a flexibility in how you draw these molecules. That's why when I post my answers, I say possible solutions. Let's see what the answer key says here. Answer key gives B as the answer, and as you can see, we have the numbering as we did before. Remember to go in this direction because here is your double bond. And here's your ethyl group, here's your methyl group in position number 3 for the ethyl and number 5 for the methyl. So this is your answer B. Let us turn our attention now to alkynes. Notice a Y. Alkynes are hydrocarbons that contain one or more carbon-carbon triple bond. Keyword here, triple bond. For this course, we'll just use one. So we'll say molecules that have one carbon-carbon triple bond. Of course, as you can imagine here, this is the simplest because we have two hydrogens bonded to the carbons of the triple bond. And of course, this molecule is known as acetylene. It's the main gas in torch. When it is oxidized in presence of oxygen, you get a real high temperature. So that's why it's used in welding torches. Based on the VSEPR theory, valence shell electron pair repulsion theory, where electrons repel each other. So these electrons here and these electrons here are repelling each other, making this bond angle here 180 degrees. So it is a linear molecule. And as you can expect, there is no cis and trans isomers around the alkyne functionality. So there's no cis and trans isomers. So let us see how we name alkynes. We go right into the naming of alkynes since we will not have isomers of alkynes. So what we'll have to do here is, for the corresponding alkane, we change the A to a Y. Alkyne. Make sure again you write the Y so we can read it when we grade. So let us apply that to naming this molecule here. We identify it as an alkyne because it has a carbon-carbon triple bond. Make sure you make that observation. Then you start numbering at the end closest to the triple bond. Start numbering at the end closest to the triple bond and go in the direction of the triple bond. So this becomes 1, 2, 3, 4, 5, and 6. 6, as you know, corresponds to hexane. We change the A to Y, so here is the Y. So this Y is indicating that there is an alkyne or a triple bond present in the molecule. To be more specific, it's a carbon-carbon triple bond in the molecule. It's in position number 2. Notice it's the first carbon of the numbering that's placed here. So this 2 represents the location of the triple bond. Why 2 and not 3? Because we're numbering in this direction. So this is the first carbon of the triple bond and it's in position number 2. So that's why we put a 2 here to represent or to illustrate and demonstrate that it's an alkyne and it's in position number 2. Let us look at branched alkynes. I hope you can see now that organic chemistry is getting easier. because once you understand the concept, it's just a matter of applying it to different molecules. So let's apply the nomenclature to branched alkynes. Notice again the Y, alkynes, a triple bond. Here is a alkyne. Why? Because we have a triple bond here. We start numbering at the end closest to the alkyne, and we go in this direction. 6 carbons, because we have 1, 2, 3, 4, 5, and 6. Notice there's a methyl group here on carbon number 5. And there is a triple bond here in position number 2, which is indicated by this Y right here. So now you can see why chemistry is a science and it's so precise. That's why we take off points if you do not put a Y, and if you put an A or an E, we subtract points, because it's a very precise science, organic chemistry is. So this 2 represents this position of the first carbon of the triple bond for the numbering sequence. This 5 represents the position of the methyl group, which is right here. So this is the name. Your job is to give the name of a molecule like this, give the IUPAC name using a systematic method. That's why science is a systematic way of learning information. Identify the functional group. It's a triple bond. Here's a carbon. This is the line angle representation, so you won't see a carbon here. And because it's linear, it's just assumed that it's there. So this is carbon number 1 right here. Carbon number 2 is right here. Carbon number 3 is right here. Number 4 and number 5. So that's a pentene. It's a triple bond as indicated with the Y, and it's in position number 2. Notice we're starting at this end this time because the triple bond is closest to this end and not this end. There is a methyl group right here, CH3. Why methyl? Because it's 1 carbon. And 1 carbon corresponds to methane, and the word is methyl if it's used as part of the name. So this methyl group is right here, and it's in position number 4 of that numbering. So it's become 4-methyl. Remember that we separate numbers from letters with a dash. So let us apply this knowledge. So what is the structure? This time we have to give the structure of this molecule here. So look at that molecule carefully and identify something about it. The first thing that you should identify here is that Y. So it has a triple bond. So right away you can rule that out. It has 5 carbons because it's a pentene. So it has 1, 2, 3 as a triple bond and 5 carbons, and this is in position number 2. So obviously we have a carbon here, and this is 1, 2, 3, 4, and 5. So this would be 2-pentene. But there is a methyl group on carbon number 4. Here's carbon number 4. So there's a methyl group here. So this should be the molecule. So we know right away that this will not work because this is 1, 2, 3, 4, 5, and 6. 6 carbons won't work. This is 1, 2, 3, 4, and 5. Looks reasonable, but it does not have the 4-methyl. So more than likely this is it. So let's see what's on the next slide. So you can see here this is it, because we have 1, 2, 3, 4, and 5, and on number 4 is our methyl group. Number 2, carbon number 2 has the triple bond. Don't forget, that's a carbon and that's a carbon. So this becomes the structure given that IUPAC name. You should be able to think in reverse. So if given this structure, can you give the correct name? Again, identify the functional group, triple bond, right here. Start numbering at the end closest to it. So this would be 1, 2, 3, 4. Notice I would not go here because I need my longest chain. So I go here 5 and 6. So this becomes a branch. Okay, so let's see if we can put this together. So what we need here is 6-hexyne. So as you can see, this will not work because that's a pentyne. This will not work because that's a pentyne. Has only 5 carbons in the longest chain. So it's one of these, either A or B. Let's see which one is reasonable. So we have here, let's look at this one first. 3-methyl. But this methyl group is on carbon number 4. So right away we see that won't work. Let's look at this one. 4-methyl looks good. 2-hexyne. Remember the Y is for the double bond and it's in position number 2. So it would appear that that is the correct answer. Let's see what's on the next slide. And here it is. So we start numbering 1, 2, 3, 4, 5, and 6. Again, this becomes the longest chain that has the triple bond, and this is a branch. And that branch is on number 4, and it's a methyl group. This 2 represents the position of the triple bond, and the Y represents the triple bond. So with that, you should be able to name alkynes, and if given the name of an alkyne, you should be able to give the structure of an alkyne. Some more examples before we close. So let's look at this one. How do you name this molecule? Let's look at the line angle here, since that's more what we'll use in this course. So here's a triple bond. Here's carbon number 1. Don't forget there's a carbon right here. 2, 3, 4. So it's a butyne. The Y represents the triple bond. The 1 represents the location of the triple bond. And of course the 3 represents the methyl group, which is right here. Same for this molecule. Here's a triple bond. So it's an alkyne. Do we start at this end or at this end? Obviously we start at this end because this end is closest to the triple bond. So we have 7 carbons. Heptyne, we indicate a Y. We use a Y to indicate the presence of a triple bond, and we use a number to indicate the presence, the location of the triple bond. It's in position number 3 right here. And over here we have 2 dimethyl groups, so it's a dimethyl, and it's on carbon number 6. So that's why we use a 6, 6. Remember, don't forget, use 2 numbers if it's a di. Of course, if we have three of the same, we'll use three numbers to indicate that there are three groups. Okay, lastly, let us look at the properties of alkenes and alkynes. They are nonpolar molecule, as you can imagine, because it consists primarily of, well, it consists entirely of carbons and hydrogens. And as we said in the previous chapter, they have just about the same electronegativity, so therefore the bond polarities are pretty similar, and it's not polar. They do not have polar covalent bonds. So alkenes and alkynes are non-polar molecules. The attractions between the molecules are basically van der Waals. So you will not find hydrogen bonding or dipole-dipole. There are London dispersion similar to what we encountered in alkanes. The physical properties, as you can expect, are similar to alkanes, as stated here. Alkenes and alkynes are insoluble in water. So in other words, remember, water is a polar solvent, and alkenes and alkynes are non-polar molecules, and we are using the comparison here that like dissolves like. So polar molecules such as water will dissolve a polar solute such as sodium chloride. And non-polar solvent such as a hydrocarbon, an alkane, will dissolve a non-polar molecule solute such as an alkene or an alkyne. That's why they are insoluble in water but soluble in another non-polar organic solvent such as cyclohexane. Alkenes and alkynes that are liquid or solid at room temperature are less dense than water. So you'd expect it to float on water. So if you mix water and an alkyne and shake it up, you'd expect to find the alkyne at the top and the water at the bottom, because water is more dense than these alkenes and alkynes. I think this is the last slide, and yes, it is the last slide. So once again, take your time and go through these slides. I will also post the PowerPoints on the announcements of D2L. We have an exam coming up this week, which is Thursday the 11th. Material from this lecture will be on that exam, just the nomenclature of alkenes and alkynes and everything that we've covered up to this point. So look out for the tutorial that I'll post in a few minutes, and remember they will be due on Wednesday, just prior to you taking the exam. The idea here is that you get the practice from the tutorial questions so you'll be ready for the exam on Thursday. So once again, continue to study hard and get ready for the exam on Thursday. Okay? Bye.